Hello and welcome. Today we're going to take a look at the phenomenon of electrostatic discharge, or ESD, and how it affects integrated circuits. Electrostatic discharge is just one of an entire range of phenomena that come under the heading of electromagnetic compatibility, or EMC for short. Now, simply put, the study of EMC concerns itself with how an electronic device responds to electromagnetic disturbances, and how an electronic device might disturb other devices through its own electromagnetic emissions. Most frequently, we study how a device responds to radiated energy and conducted energy over a range of frequencies, and how much energy a device radiates as radio waves and launches on attached conductors. Frequently, we'll look at a specific type of conducted energy known as electrical fast transient, or EFT, and that's a particularly difficult kind of conducted interference that's caused by some fluorescent lamp fixtures and other electrical equipment. Modern microcontroller-based devices have to be able to tolerate this kind of interference without damage and without resetting. But today, we're going to be looking at another sticky form of electromagnetic interference, electrostatic discharge. Now, to begin with, let's have a look at what ESD actually is. The most obvious and the most spectacular example of electrostatic discharge is lightning. In many parts of the world, some seasons bring thunderstorms, and those storms frequently present us with beautiful displays of the awesome power of lightning. Lightning results when friction between ascending and descending atmospheric currents in a storm cloud cause electric charges to segregate into different areas. Now, as these charges accumulate, the likelihood of an electrostatic discharge increases, and when the discharge occurs, you get the phenomena you normally associate with lightning: a bright flash of light as the electron flow ionizes and heats the air into incandescence, and the sound of thunder as the superheated air explosively expands. Now, let's think about lightning a little more closely. You have a segregation of charges of opposite polarity and an insulating dielectric layer, the air. When the charge potential becomes too great, the air dielectric breaks down and the air is ionized. That is, the electrons are stripped from the molecules that make up the air, and the result is a superheated plasma. Of course, when the electric strike is over, the air cools, the electrons resume their normal orbits, and all is well. That is, unless you happen to be in the vicinity of the lightning strike. Okay, now, let's think smaller. When the humidity is low, most of us have had the experience of walking across a carpet, reaching for a doorknob, and zap! Boy, that really hurts. The same thing has happened. A charge difference between the doorknob and your body, which, by the way, is actually quite conductive, has resulted in an electrostatic discharge event. The air was ionized. A sound was heard as the air superheated and expanded. The same kind of thing can happen to integrated circuits, but there are a couple of differences. The dielectric isn't air, it's silicon dioxide, or glass, and the glass can't repair itself like the air can. Let's think about what happens inside an integrated circuit when an ESD event occurs. Well, the first thing, there probably isn't going to be a spark. And to understand why, we need to think about the structure of a MOS transistor. A MOS transistor consists of a channel that can be either conducting or non-conducting. The state of the channel is controlled by a gate electrode that is electrically isolated from the channel by a thin layer of silicon dioxide. The electric field caused by the potential of the gate relative to the potential of the channel controls the flow of current in the channel. All well and good. But to maximize the influence of the electric field on the channel, that gate insulator has to be thin, perhaps as thin as 10 nanometers. So that's the struggle. We need to get a gate insulator as thin as it can be, but also with as much dielectric strength as possible. Okay, it's time to break out the math. First, think about air. The dielectric strength of dry air is about 36,000 volts per centimeter. So think about that for a second. If you draw a half-centimeter arc when your finger approaches a doorknob, you've probably experienced a potential difference of close to 20,000 volts. Great job! Well, for silicon dioxide, as it appears in semiconductor materials, the dielectric strength is on the order of 10 million volts per centimeter. Well, that should surely be enough, one would think. Well, the problem is that 10 nanometers is 1/1,000,000th of a centimeter. That means that the gate can tolerate at most about 10 volts before it breaks down. And since we've already seen that your body can accumulate over 10,000 volts of potential, it's easy to see that you're pretty likely to cause a dielectric breakdown in any unprotected gate just by routine handling. Well, that's okay, right? Because when a lightning strike occurs, the air heals itself. Doesn't silicon dioxide do the same thing? Good try, but no. See, here's the thing. In air, the discharge path leaves a trail of ionized oxygen and nitrogen. Some of the ionized oxygen forms ozone, giving you that nice after-a-shower smell. And some of the ionized nitrogen forms oxides of nitrogen, and that's good for the flowers. In any case, natural processes cause the compounds to dissipate over time, and soon the air returns to normal. No harm, no foul. But in solids, the situation is quite different. Electrostatic discharge causes localized heating that exceeds the melting point of the dielectric material, in this case, glass. This damage can destroy the functionality of a semiconductor device in two ways. First, for just an instant during the discharge event, the conduction path is carrying a tremendous current. This current can vaporize the tiny conductors etched into the active layers of the chip. Suddenly, where you had a conduction path before, you have none, and the device stops working. The second failure path is called punch-through. It's when the gate oxide melts along with parts of the metal gate, and the molten metal and glass short the connection between the gate and the conduction channel of the MOS transistor. Effectively, the transistor can no longer switch, and once again the device stops working. Now, sometimes an ESD event doesn't actually destroy the part. In some cases, it can just diminish the performance of the device. If the gate of the transistor is compromised, the gain may be reduced, or the threshold voltages might be altered. Hey, even worse, you might not see any reduction in the performance in the near term, but the device may have less ability to tolerate another ESD event in the future. You won't even know about it until suddenly, for no apparent reason, the device just stops working. The culprit in all this is something called the triboelectric effect. The prefix tribo comes from a Greek word that means to rub. When two dissimilar materials come into contact, they're likely to exchange electrons. Then when they're separated, one of the materials is chemically more likely to retain the electrons than the other, so that material becomes negatively charged. The other material, the one that lost the electrons, becomes positively charged. This table gives you an idea of various materials and their tendency to gain or lose electrons. But this isn't an exact science. The amount of charge transferred depends a lot on the surface texture, contamination that may be present, humidity, and a whole number of other factors. The thing to remember is this: static electricity isn't just a matter of leather shoes on carpet or running combs through dry hair. Damaging charges can accumulate on any surface at any time, and as we've seen, just because you don't see a spark doesn't mean you're safe. So, let's get this straight. Electrostatic discharge at levels far too low to actually cause a spark can damage or destroy MOS transistors. And you can't get away from static electricity due to the triboelectric effect that's all around us. So, what can we do? Well, as it turns out, there's actually quite a lot that we can do. First, all modern semiconductor devices, with some rare exceptions, include structures that mitigate the risk of electrostatic discharge. Now, notice that I said mitigate and not eliminate. You can still overwhelm the protection circuitry with enough electrostatic energy, but these protection mechanisms are a vast improvement over exposing an unprotected MOS gate to the outside world. Now, in this diagram, we see two different kinds of protection. Connected to the I/O pin, in addition to the internal circuitry, is a pair of diodes. One connected to the power supply rail and the other to ground. Now, since the diodes are reverse biased, you might initially think that they have no effect other than to add a little capacitance to the input stage. But in fact, they're critical. If a voltage surge that exceeds the supply level is applied to the I/O pin, the upper diode will begin to conduct, limiting the voltage to the internal circuitry to no more than one diode drop above the supply rail. Now, similarly, if a surge that drives the I/O pin below ground is applied, the lower diode begins to conduct, limiting the voltage to the internal circuitry to not more than one diode drop below ground. Now, there are other considerations for these diodes that we're going to talk about in just a moment, but for now, understand that having these diodes in place goes a long way toward protecting the sensitive gate oxide in the internal circuitry. But what if the supply pin is the point that takes the surge? Well, that's why we have the power clamp in the circuit. This device, frequently some kind of transient voltage suppressor, works like a bidirectional Zener diode, conducting when the voltage exceeds some predetermined level. Now, it's often designed to dissipate a level of energy that would damage or destroy the sensitive logic circuits that make the chip work. Once again, the power clamp can be overwhelmed by excessive energy, but it's a lot better than leaving the device completely unprotected. Now, here's a closer look, and it gives us the opportunity to see the characteristics we need in the protection diodes. Consider what happens when a surge due to electrostatic potential comes along. If the surge is positive relative to the power rail, the upper of the two diodes conducts, and the current associated with the surge flows into the power rail. But for this to work, the switching time of the diode has to be significantly less than the expected rise time of the ESD event. If it's not, the diode will still be in the off state when the surge is at the peak of its destructive potential, and the MOS input will invariably be damaged. So that's the first requirement. The diode has to be fast. The second requirement is that the diode has to be robust. By this, I mean that the diode itself mustn't be damaged or destroyed by the kind of ESD events we expect to see. If the diode is destroyed, it can't protect the input. On the chip, the diode structure might wind up being quite large compared to some of the other device components, just to allow it to handle the expected currents. Now, the last two requirements really don't have anything to do with ESD protection, but they do concern compromising device operation when there isn't any ESD event. You see, many inputs are expected to operate at high frequencies, maybe hundreds of megahertz, perhaps as high as a few gigahertz. That means a few picofarads of additional capacitance on the input can have a significant impact on the device parametrics. So for this reason, we have to keep the parasitic capacitance of the protection diodes as low as possible. Finally, we have to recognize that many electronic components go into applications that are power constrained. Now, I'm thinking about battery-operated components, especially those that have to operate for months or years on battery power. Minimizing current draw is crucial, and that means the reverse bias leakage of these diodes had better be as close to zero as can be achieved. So to summarize, these protection diodes have to be fast. They have to act quickly to route the ESD surge current away from the internal circuitry. They have to be robust so that they can handle the ESD current. They have to be extremely low leakage. Hey, if the diodes are leaky, they'll impact battery life. And if that input connects to analog circuitry, just a little leakage current can disturb the accuracy of a low-level sensor. And the diodes have to have a very low junction capacitance. Otherwise, you've just introduced a low-pass filter into your circuit. Here's a diagram of a typical I/O pad structure in a Maxim device. You can see the pad, the input resistor, and the diode structures quite clearly. But what you can't see is the care with which Maxim manages the layer stack and the fabrication process. All of these things contribute to the overall success of our ESD strategy. Now, Maxim also provides ESD protection devices that let our customers provide an extra level of ESD mitigation to circuits that extend beyond the board edge. Our customers count on Maxim to help reduce the risk of failure due to ESD at every step of the product flow, from device inception and design through device manufacture and delivery, and finally, in their end product. To that end, Maxim protects our devices from ESD damage at every step of the process. As wafers, we employ carriers that are constructed from static dissipative materials. This material ensures that no static charge will be accumulated on the materials surrounding the wafer, and it reduces the likelihood that the wafer itself will accumulate a charge. When we deliver parts to customers, we provide them in packaging that is static dissipative. That ensures the parts will arrive in the same excellent condition as when they left our factories. Now, one note about packing material. There is anti-static material, and then there is static dissipative material, and they're not the same. Anti-static material won't accumulate a static charge, but it doesn't protect the contents from a static discharge. Static dissipative or conductive materials, on the other hand, do protect the contents from static discharge. Anti-static material is often pink in color, while static dissipative materials are often black or dark and appear metallic, frequently because they do include a thin metallic layer. But be careful, not every black or metallic-looking material is static dissipative. Look for a logo or other indication on the package before you use it. When you're working with sensitive parts, prevention of ESD damage has to be the rule. Now, you don't have to dress up quite like this fellow, but there are good common sense measures you can take to make sure all your hard work doesn't end up the victim of an ESD event. Let's start with a work surface. Use a static dissipative mat that's properly grounded. That work surface forms a baseline on which everything else rests. Your equipment needs to be static safe too. Now, all modern soldering stations use a 3-wire grounding system, but be sure yours is also labeled as ESD safe. That guarantees that the mat and the soldering handpiece are going to be at the same potential. An ionizer is a helpful accessory. This device ensures that the air around the workstation contains a concentration of free ions that tend to neutralize accumulated static charges. Better to neutralize them before they can do something terrible. Okay, so that's the stuff around you, but what about you? Well, first, wear a wrist strap. The human body is quite electrically conductive, so a wrist strap that connects your body to the grounding system through a large resistor is sufficient to dissipate any charges you may have accumulated as you walk up to the workstation. A large resistor in the wrist strap keeps you safe by limiting the amount of current that can flow through your body if you happen to come into contact with something that's at a high potential. Never just ground your body through a metal strap. That's extremely dangerous, and you could be electrocuted if you come into contact with an exposed high voltage. Now, a word about clothing. You really don't have to don a bunny suit like this fellow, but you should pay attention to what you wear around a static safe workstation. Natural plant-based fabrics like cotton or linen are good choices because they don't tend to accumulate static charges as rapidly as some other fabrics like silk. Now, synthetic fabrics, nylon, rayon, and other similar materials, they're the worst. In this picture, our hero is wearing ESD safe shoes, but you can get the same effect by wearing heel straps. These attach to the back of your shoes, and a strap goes under your sock to contact your skin. And if the floor is not ESD safe, then you should have an ESD safe mat to stand on. If you have chairs, they should be ESD safe as well, usually with a chain that contacts the floor. You see, you really do have to think ahead when your job is to deliver the best parts in the world with the lowest failure rate. Now, we've talked about the dangers of ESD and how to mitigate those risks, but how do we actually ensure that our devices have some level of resistance to ESD events? That is, how do we actually quantify ESD safety? Well, that's not an easy question because every ESD event is going to be a little bit different, and every object that carries a charge might deliver it to a sensitive part in a slightly different way. But we've learned that ESD events have elements in common, so we can build a model that describes how ESD events typically happen. Or rather, we can build several models. Now, the most commonly quoted model is the so-called human body model, or HBM. This model describes a typical ESD event that might occur when a human body part, let's say a finger, comes in contact with a sensitive device input. The human body model is the most frequently quoted ESD model, but it's not the only one. The air gap discharge model is a model given by the IEC that's similar to the human body model, but it involves a lower resistance and a larger capacitance. That is, there's a larger charge that's conducted more rapidly to the device under test than under the HBM. Now, the human body model recognizes that the human body has an inherent resistance. The discharge path in the HBM is limited by a resistor. But if the discharge path is not through a human body, but let's say through metal-on-metal contact, then that limitation doesn't really apply. And that's why we also employ the machine model, or the MM. The machine model eliminates the resistor and substitutes a small inductor to more accurately model the case when charged metal touches a pin. And then finally, there's the charged device model. This accounts for the case in which the device under test itself might accumulate a charge by sliding down a dispensing tube, for example. If the device picks up a charge, then lands on a grounded work surface, there will be an electrostatic discharge. The test case for the CDM involves applying the potential to a plate on which the device under test is resting on its back. The pin under test is then grounded through a 1 ohm resistor. Now, as you might surmise, the human body model attempts to describe what happens when a human body makes contact with the device pin. The human body, in this case, is modeled with a 100 picofarad capacitor that's charged to the test voltage. When the switch is thrown, the capacitor is discharged through a 1500 ohm resistor to the device pin. The JEDEC standard on which the HBM is based specifies one discharge with positive polarity and one discharge with negative polarity at a voltage no less than 2000 volts. The air gap model is based on an IEC standard that looks a lot like the HBM test arrangement. The primary difference is that the capacitor is larger, 150 picofarads versus 100, and the series resistor is a lot smaller, just 330 ohms versus 1500 ohms. That means the circuit can deliver a lot more current to the device under test than the human body model circuit. Now, in addition, the air gap model applies 3 pulses in each polarity, not just 1. Well, needless to say, the air gap model is much tougher than the HBM, but in some applications, adherence to the IEC standard at some reference voltage is becoming a requirement. Now, at first glance, the machine model test arrangement looks a lot like the HBM and the AGM configurations. A high voltage source charges a capacitor, which is switched to dump the charge onto the device under test. The difference here is that instead of a resistor, the discharge occurs through a 500 nanohenry inductor. This arrangement simulates a metal-to-metal contact, and the discharge of the capacitor through an inductor gives the characteristic ringing that you see in the waveform. The voltage applied in an MM test is much lower than that applied in an HBM or an AGM test, typically about 200 volts versus several thousand volts in an HBM test. But since there is no current limiting resistor, the delivered current pulse can be quite aggressive. Now, while you'll still see the machine model mentioned, you ought to know that JEDEC has discontinued the use of the machine model, and the ESD Association, an industry standards group, has argued in favor of its abandonment by the industry. Finally, the charged device model, or CDM, simulates the situation where the IC has slid down a dispensing tube onto a grounded platform. During the journey down the tube, the IC may have picked up a significant charge, and when it hits the grounded surface, it may experience an unpleasant discharge event. In this arrangement, the IC is placed, pins up, on a dielectric sheet that covers a metal plate. The metal plate is charged up to the test voltage, and then the pin under test is touched by a grounded probe. Frequently, the probe is actually grounded through a 1 ohm resistor, and the signal from the probe is routed to a high-speed oscilloscope to gain insight into the current delivered to the node. Maxim's requirement for this test is over 700 volts for corner pins and 500 volts for all other pins, but the industry is beginning to move toward an understanding that less voltage, frequently about 250 volts, is sufficient to validate this test case. Different Maxim parts will have different ESD protection levels. So where can you find this information? Well, the answer is right there in the datasheet. Just look under the absolute maximum rating section. Now, unless there's a very good reason to use a different model, we'll specify the ESD rating using the human body model, and we'll generally give the value in kilovolts. In this datasheet, we indicate the part will survive a positive or negative ESD event of up to 15 kilovolts based on the human body model. Now, of course, just because the device has ESD protection, you should still use appropriate precautions when you handle the devices to prevent damage.
Thank you for watching this video. For more information on this topic, please go to our website at www.maximintegrated.com under Products, Interface, Signal Line Protection ICs. We hope you enjoyed this video and see you again in another educational video of Maxim Integrated.